Hello students, welcome to my channel Engineers Academy. Let's solve this one another problem from the distributed loads topic. Again, in this problem we are required to calculate the supporting reactions at A and B for the beam subjected to the two linearly distributed loads, right? So we have this beam and it is subjected to this two linearly distributed loads, right? So what we will do is that we will replace these two distributed loads by only one concentrated load, right? There are two methods to solve this particular problem, right? So one method is that you people can replace this one distributed load by a single resistant, and you people can replace this distributed load by a single resultant, right? And the second method is that we can replace this whole distributed load by a only one single resultant, right? So I will try to solve this problem by using the two methods, right? So first I will replace this whole distributed load by a single resultant, right? So for that, what we can do, we can apply the principle of moments equation that we applied to determine the centroid of a given area, right? So what that principle of moment equation says, that moment of the resultant is equal to moment of all forces, right? So what does this mean, right? So we can write that this will be, let's say that if you want to find the moment of the resultant of all these distributed loads about this point A, right? So let's say that the resultant of these distributed loads is located somewhere here. Let's say that this is the overall resultant of all these distributed loads. So let's say that the distance of this resultant from that point A is, let's say this distance is, let's say x bar, let's say. So the moment produced by this r about that point A will be x bar into r, right? And this will be equal to, now if we replace these distributed loads by their respective resultants, right? So further we can divide these distributed loads into four sub areas, right? So we can say that we are having this one area, let's say, and then we have this one another area. We have two triangular areas and two rectangular areas. So let's say this is area 1, this is, let's say, area 2, and this is, let's say, area 3, and this is, let's say, area 4. So we can replace this distributed load of area 1 by resultant R1, right? Let's say that the resultant of this area 1 is located somewhere here, let's say, and the resultant of this area 2 is located somewhere here, let's say, right? Let me call it this one is R1, this one is R2, and let's say the resultant of this area 3 is located somewhere here, let's say, that will be somewhere here. So let's say this is R3, and the resultant of this 4 area, this rectangular area, is, let's say, somewhere here. Let me represent that as well, right? So let's say it is somewhere here. So this is R4, right? So the moment of the resultant will be equal to the moment, or the summation of the moment of R1, R2, R3 and R4. So we can write that this is, and let's say that R1 is at a distance of x1, let's say this is x1, and let's say R2 is at a distance of x2 from point A, and let's say R3 is at a distance of x3 from point A, let's say this is x3, and let's say that R4 is at a distance of x4. So then the moment produced by R1, R2 and R3 will be equal to, so we can write that this will be x1 R1, this is the moment produced by the R1 resultant, and similarly we can write x2 R2 plus x3 R3, and similarly plus x4 R4, right? And since R is the resultant of all these, so we can write that R will be equal to, or we can say that this x bar will be equal to the summation of all the moments divided by the resultant, and the resultant is equal to R1 plus R2 plus R3 plus R4, right? So this means that if we want to represent this whole distributed load by a single resultant pointed load, so then we can apply this formula, right? And this x bar will give us the position of that overall resultant of all these distributed loads from that point A, right? So then we can find this x bar by applying this formula, and R is equal to this thing, right? So we will try to use this equation, and this is again that principle of moment equation, right? So if I write this in generalized form, so then this will be x bar into while using this formula for the centroid, we used to write x bar times area, and this was equal to the integration, and this was xc times dA, right? So what does this mean? Now here the area, so the R1 is equal to the area of this rectangle 1, right? So this means that now the areas are the resultant forces, right? So now we can replace this area by R, right? So this is x bar into R, and this, since again this dA will be now in this particular case dA is equal to dR, right? Since if we consider this rectangular area, and if we consider a differential part of this rectangular area, so then that will be if let me draw it here, if we consider this differential area, so then this will be equal to this dx into height, which is this intensity, right? And so I can write that dx, which is in the units of dx is in meters, right? Let me write the units in meters, and this intensity is 4 kilonewton per meter, right? So I will write 4 kilonewton per meter. So this meter will cancel out. So the area, that differential area is equal to, now the units are force units, right? So then this is 4 dx kilonewton, right? So this means that now while solving these distributed loads problems, the areas of all these distributed loads will give us the forces, the resultant forces, right? So this means that this is, we can write that this is xc into dr, right? And the summation of xc into dr, so this xc into dr is the moment, and this integration means that the summation of all the moments of all the resultants of these 4 areas, right? So further we can simplify this equation, we can generalize this equation as x bar into r, and this will be equal to summation of x1, this is xn rn, and we can say that n starts from 1 until infinity, right? And we can find this x bar equals to, this is the n equals to 1 until infinity xn rn divided by the whole resultant, and then we can say that this resultant is equal to the summation of all rn's, that is n equals to 1 until infinity. So now we can simplify this equation that x bar equals to summation of n start from 1 until infinity, this is xn rn divided by rn, the summation of rn, this is the summation of rn, this is right, and we can write that this is, so now this is that generalized equation, right? Now we will use that equation. Let me write that equation here again, right? So x bar will be equal to x1 r1 plus x2 r2 plus x3 r3 plus x4 r4 divided by r1 plus r2 plus r3 plus r4, right? So now what we will do is that we will find this x1, x2, x3 and x4, and these x1, x2 and x3 and x4 are the distances of r1, the resultant of area 1, the resultant of area 2, the resultant of area 3 and the resultant of area 4 from that point A respectively, right? So if I locate the resultant of this area 1, so that resultant will be at the geometric center of this rectangular area, right? So let's say that the geometric center is somewhere here, right? So this is, let's say, R1. So first we will find R1 magnitude. So R1 magnitude will be equal to the area of this area 1, right? So this area 1 is rectangle, so it is 4 into 4. So I will write that this is 4 into 4. So this R1 equals to 16 kilonewton, right? This is 4 meters into kilonewton per meter. So meter will cancel out, so we will be left with the units of kilonewton. And again, this area gives us the force, resultant force, and the units are of kilonewton, right? Similarly, the distance of this R1 from that point A is, let's say, this distance is x1. So this x1, let me write it here, that x1 is equal to half of this 4 meter length, right? So this is half of 4. So this will be equal to 2 meters. Similarly, we can find R2. So the resultant of this area 2 is, let's say, located somewhere here, and this area 2 is triangular area. So the distance of this R2 from this point A is, this will be, this is x2. So x2 will be, let me first find this R2. So R2 will be equal to the area of this triangle 2, right? So we can write this is half, this base is 4 meters, and this height. So now what is this height, right? This overall height is 8 kilonewton per meter, right? This overall height is 8 kilonewton per meter, but this height will be 8 minus 4, right? So this means that the height of this area 2 is 4 kilonewton. So I will multiply this with 4, right? So this is 8 kilonewton. So we can write that R2 is 8 kilonewton, and x2 is equal to 2/3 of this length, right? So we can write that this is 2/3 into 4, right? So this we know that the centroid of triangular area is located at a distance of 2/3 from this apex along this line, right? So this is x2, and this will be 2 divided by 3 into 4. So this is 2.67, right? So x2 is 2.67 meters. So this means that R2 is located at a distance of 2.67 meters from that point A. Similarly, the resultant of this area 3 is, let's say, located somewhere here. This is R3, and this is the distance of this R3 from that point A, and let's say that this length is x3, right? This blue length is x3. So now first I will find this R3 resultant. So R3 is equal to the area of this triangle, right? So we can add, this is half, and the base is 3, and the height. So this whole height is 10 kilonewton per meter, but we need to have this height, right? So this height will be, the height of this area 3 will be 10 kilonewton minus 2 kilonewton per meter. So this is 8. So I will multiply this with 8, right? So this is 12 kilonewton. So R3 is 12 kilonewton, and x3 will be equal to, so x3, we can divide this x3 into 2 dimensions, 2 sub lengths, right? So this x3 will be equal to this 4 meter length plus this small length, right? Let me represent that length as well, plus this length. So 4 plus this length, right? So I will write that 4, x3 is 4 plus this length is 1/3 of this 3 meters, remember, right? So the centroid of a triangular area is 1/3 of this length from this edge, and 2/3 of this length from this apex, right? So now we are measuring this distance. So then this is the 1/3 of this length from this side of this triangle, right? So we can write that this is 1/3 of 3 meters. So this will cancel out. So this is 4 plus 1. So this means that x3 is equal to 5 meters. And similarly, let's say that R4 is located somewhere here. Let's say that this is R4, and this R4 will pass through the geometric center of this area 4, that is the centroid of this area 4, right? So this is R4. So then let's say that this R4 is at a distance of x4. This is x4, right? So this x4 is again equal to 4 meters plus this small length plus this length. So then this is x4. So then we can find R4. So R4 is equal to the area of this rectangle, which is 3 into 2. So I will write this is 3 into 2. So this is 6 kilonewton, and x4 is equal to this 4 length plus this length. So 4 plus this length will be the half of this 3 meters, since this R4 will pass through the centroid of this rectangular area, and the centroid of this rectangular area is located at the geometric center of this rectangle, right? So then that will be half of that 3 meters length. So then we can write that x4 will be equal to 4 plus 1.5. So this is 5.5 meters. And remember that these x1, x2 and x3 are all made from that point A. This is very important, right? So now we can apply this equation 1. So that this equation 1 will give us this x bar, right? So this is, let me find this x bar. So x bar will be equal to x1. So x1 is 2 meters into R1, which is 16, plus x2 is 2.67 into R2, which is 8, x3 is 5 and R3 is 12, x4 is 5.5 and R4 is 6, and divided by the summation of all the resultants, right? So this is 16 plus 8 plus 12 plus 6. So 2 into 16 is 32 plus 2.67 into 8 plus 5 into 12 plus 5.5 into 6. So this gives us 146.36. And this gives us 42 kilonewton, right? So the whole resultant is 42 kilonewton. So now if we divide this, so this is 146.36 answer divided by 42. This is x bar is 3.485. Let me write it as x bar is equal to 3.485 meters, right? So now we can replace all this distributed load by a single pointed load, right? So let me draw the free body diagram now, right? So this will be our free body diagram. So here at this point A, we will have two forces, two reaction forces. So let's say this is AX, and here we will have that AY. And here, since at point B we have the roller support, so this is RB, or we can say this is B, and the resultant of all these distributed load is equal to 42. The summation of R1 plus R2 plus R3 and plus R4 is 42 kilonewton, and it is located at a distance of 3.485 meters from that point A. So let me draw that force, that is somewhere here. This is R equals to 42 kilonewton, and this distance of this resultant from that point A is 3.485 meters. So now this problem is quite simple, right? We can find this AX, AY and B which are required, right? Now if I apply the summation of moment about point A equals to 0, so as we can see that this AX and AY are crossing through that point A, so they will not produce the moment about that point A. This B reaction is producing the counterclockwise moment about that point A, and the distance of this B from that point A is 7 meters, since the whole length of this beam is 4 plus 3, so this is 7 meters. So this will be 7 times B, 7 into B, and this R is producing the clockwise moment, so I will write minus is 42, and the perpendicular distance, the moment arm of this resultant from that point A is 3.485. This is equal to 0, or we can say that 7B equals to 42 into 3.485, or we can divide both sides by 7, so that will give us that reaction at the roller support. So this is 42 into 3.485 divided by 7, so this is 20.91. so B equals to 20.9 kilonewton, right? And similarly, now if we apply the summation of forces along x equals to 0, so as we can see that this x is acting in the x direction, right? If this is our positive x and y direction, so only this x is acting in the positive x direction or in the x direction, so this means that x is equal to 0. There is no other force in the x direction. And similarly, if we apply the summation of forces along y equals to 0, so ay is acting in the positive y direction, so I will write ay. This r is acting in the negative y direction, and b is acting in the positive y direction, which is 20.9, and this is equal to 0. So ay equals to 42 minus 20.9, so 42 minus 20.9, so this is ay, which is 21.1. so ay equals to 21.1 kilonewton. So now the total resultant at point A is equal to ax square plus ay square, and then we have to take the square root, but ax is 0, so if ax is equal to 0, so the total resultant reaction at A is equal to ay, which is equal to 21.1 kilonewton, and the resultant reaction at point B is 20.9 kilonewton, right? So this is one method of solving this particular problem. The second method, in the second method, what we will do is that we will not replace all these resultants R1, R2, R3 and R4 by this single resultant. We will keep these R1, R2, R3 and R4 at these particular distances x1, x2, x3 and x4, and then we will apply that summation of moment about point A equals to 0, and then the summation of forces along x equals to 0 and the summation of forces along y equals to 0. So now if I draw the free body diagram for that second case, right, so then we will have this R1, this is, let's say that R1, this R1 has a magnitude of 16 kilonewton, and its distance from that point A is 2 meters, right? So we can represent that this length is 2 meters. This is x1. R2 is at a distance of 2.67, right? So it is somewhere here. This is R2. This is R2, and its magnitude is 8 kilonewton, and its distance from that point A is, this distance is 2.67. Let me represent that by x1 and x2, right? And these are x1, x2. Similarly, R3 is at a distance of 5 meters, right? So it is somewhere here. This is that R3, and it is at a distance of x3, right? This is that x3, and similarly R4 is at a distance of 5.5 meters, right? So it is somewhere here, right? This is R4 and its distance from that point A is x4, which is 5.5, right? So let me write here. So this is x4, right? So now we will apply the summation of moment about point A for all these resultants, and this method will give us that same answer, right? So now if I apply the summation of moment about point A equals to 0, so as we can see that this B is producing the counterclockwise moment about that point A, so I will write B, and the perpendicular distance of this B reaction from that point A is 7, and all these R1, R2, R3 and R4 are producing the clockwise moments, so we will write minus R1, so R1 is 16, and the perpendicular distance of this 16 kilonewton force R1 from that point A is x1, so this is 16 into 2. Similarly, this is R2, so R2 is producing clockwise moments, so I will write minus R2 is 8 kilonewton, and the perpendicular distance of R2 from that point A is 2.67. Similarly, R3, so R3 is 12 and it is producing clockwise moment, so we will write 12, and the perpendicular distance of this R3, the momentum of this R3 from that point A is x3, which is 5 meters. Similarly, this R4 is producing clockwise moment, so this is 6, and the perpendicular distance of this R4 from that point A is x4, which is 5.5, and this is equal to 0. Or if we bring all these 4 terms to the other side, so their signs will become positive. So then we can find it. So this will give us that same 20.9 B, right? So let me solve it. So this is 16 into 2 is 32 plus 8 into 2.67 plus 12 into 5 plus 6 into 5.5 divided by 7. So this is that 20.9. So B is 20.9 kilonewton, and if we get this B as equal to 20.9 kilonewton, if we apply the summation of forces along x equal to 0, so again Ax is only acting in the x direction, so Ax will be equal to 0, and if we apply the summation of forces along y equals to 0, so then Ay is acting in the positive y direction, and R1, R2, R3 and R4 are acting in the negative y direction, so we will write minus R1 minus R2 minus R3 minus R4, and if I take minus common, so then this will become R1 plus R2 plus R3 plus R4, and this B is acting in the positive y direction, so we will write B, and this is equal to 0. So this is Ay, and R1 plus R2 plus R3 plus R4, again if we sum up all these, so this is equal to 42, so we can write that this is minus 42, and B is this 20.9, so this is 20.9 and this is equal to 0. So if we compare this equation with this one, so both are similar equation, both are same equations, right? So this means that we will get that same Ay, which is equal to 21.1 kilonewton, right? So both these methods will give us the same answer, right? But in one method we use this equation to replace the distributed loads by a single resultant, concentrated resultant, pointed resultant, and in the second method we divide the distributed load into sub areas and then represent all those sub areas by the respective resultants, and then we apply the equilibrium equations to find the reactions at point A and B. So I hope you people would have understood both of these methods. We will apply both of these methods in the upcoming problems. So if you people think that all these videos help in your learning, so kindly subscribe my channel and like this particular video if you people want me to solve such more problems related to engineering statics.